The technique which was used to reduce the number of proposed regions so as to speed up the whole implementation timeline was called the intersection of union. Let's look at intersection of union here. Now, in this image, now you have all those 9 different anchor boxes which we talked about in the previous slide, and we have one more thing, which is the green colored box, which is the ground truth, or in normal machine learning parlance, this is the label. So this is the actual place where or actual bounding boxes for the pothole. So now intersection of union is the actual area or actual intersection, or the ratio between ratio of the area which is being intersected, that is the common areas between or anchor point and the ground truth, and the total area of both these boxes, that is the anchor point in question and the ground truth. So let's look at this the first figure here, or the first here. So which we have taken in reference to the square anchor box and the yellow one. So if you look at it, the ratio is around 0.9 here. So you can see that most of these area between the ground truth and the anchor box is kind of intersecting. So a large portion is intersecting, and therefore this ratio is higher. So, and you can see these ratios getting smaller depending on the IOU, which is the ratio of the intersection over the total over the union, which is the total area of both these anchor boxes together. The ratio as for each of these each of these different anchor boxes. So the concept of these the intersection over union and the ground truth is this. So there were certain set of rules which were defined. So any of these anchor boxes or regions of proposals which had a intersection over union greater than 0.7 was marked as a positive region, which would be taken for training, and anything which was less than 0.3 was marked as negative, or as a negative example for the training. All the others were kind of ignored. But there was one more change which was made, or one more condition which was kept here. Say suppose you don't have intersection over union of 0.7 or greater, then what was taken was in that case what was done was the largest intersection of union, the anchor box with the largest intersection of a union was taken for training. So these were some of these steps which were taken to reduce the number of proposal regions. And now we'll see now the full network, how all these different pieces, especially with these anchor boxes and the intersection over union, and all these concepts are used to finally classify and build the bounding box regressor also. Let's see that in the next slide. Now let's tie all these things which we have seen for faster RCNN together. So first we saw that you have an image, and from the image you extract features. So we have feature maps, which is basically an output from a CNN layer, any kind of CNN layer. It could be a VGG or a ResNet or any kind of CNN layer. So you get a feature maps, and on the feature maps is what we the region proposal networks. And we saw that the region proposal network, there is this concept of these anchor boxes, and these 9 different anchor boxes over the region, and then you also extract derive the intersection over union, which we saw in the previous slide. Now once these intersection of unions are taken, then this is taken into the network. So based on those positive and negative examples. Now, as we saw, the positive examples were those with the IOU or intersection of a union greater than 0.7, or it could be the if there are no proposals which are greater, which has an IOU greater than or equal to 0.7, the highest or the largest IOU was taken. And so you have a set of positive and negative examples, which were then propagated into the next layer, which is a convolution layer. And this convolution layer had two outputs, or so one was a binary classifier, as seen here, and a regressor. Now I'll come to the regressor in a minute, but let's see what is this binary classifier. Now here in this binary classifier, the classification is not done as to what kind of object is there. Here the classification is done whether it is an object or not. So and it's based on those IOU scores which were generated, and this IOU scores were called the objectness score. That is, anything with a positive who had a larger IOU, and you also had those proposals which had a lower than 0.3. So the first one was classified as a foreground, which means that there is an object there, and the second one is the background. So this is the kind of binary classification which was done, and it was all based on the ground truth which was there. The second part is the regressor. Now in this regressor, so here the regressor means you had to find the bounding boxes. So let me explain the concept of bounding boxes. So here it's not the literal x and y coordinates which is predicted here. What has been predicted here is the deltas. So I'll give you. So there are 4 different deltas which are predicted. One is the center point, like this. One of these center points of the anchor point which you are considering, which is your region of proposal, and the ground truth. Let's consider this tall anchor point, and compare it with the ground truth. Now the center point is almost the same. Say suppose this. Let's assume that the center point of the anchor point is here. So the delta which you consider is how much of distance you have to cover to get to the ground truth center point. So that is what was what was how the deltas were calculated. The other deltas were the x and y deltas. That is, from this ground truth, what was the total height in terms of difference deltas, and what was the width. So these were the kind of deltas which were calculated. So in one is the delta x center and delta y center, and then the delta width and the delta height. So these were the 4 types of regressor which were kind of predicted. So based on these the networks and the different weights, you predicted whether it is what kind of deltas were there, or what kind of deltas are there, and then based on the ground truth, the difference between this delta and the ground truth, you had this error, and which was back propagated, and that's the way training was done in this specific part of the network. That this part of the network was used for this binary classifications and also these deltas. So now after these classifications were done, then you had the next step, which is the non-maximal suppression. So as you said, as we know that you will have different anchor points which overlap each other, and these were reduced using the non-maximal suppressions. And then you have this the pooling layer also. and then it gets into the fully connected layer and the final softmax layer and the bounding box coordinate layer. So now the final softmax layer is what is the final predictions which we have, whether predicting whether it is a pothole or a signboard or vegetation, etc. So according to the different classes, you have those predictions, and the final bounding box again is the deltas, these deltas which were predicted. So, and again, after the training was done based on the ground truth. What was what were those the ground truth, and the errors were generated and then propagated back. And this was the way training was was done in this faster RCNN. So one of the greatest advantages of this faster RCNN, which you can see, is that all these moving parts are as part of a single network, and you have both the classification and the final bounding boxes which could be predicted using the faster RCNN. And these faster RCNN actually had much better timings, or much faster implementations than many of the RCNN and the fast RCNN implementations, and also the good level of accuracy also. So having seen the different types of RCNN families, we'll go ahead and implement the RCNN or the standard RCNN in this post. The faster RCNN, we will reserve it for the next post, which will be on how do we build an object detector using TensorFlow object detections, and then we will see how we can build how we will be able to build the faster RCNN using the object detector, the TensorFlow object detection API. So now let's dive into the code and then start coding and implement the traditional or the RCNN, the first version of the RCNN family, which is the RCNN in these subsequent sessions.